Okay, here's an Atwood machine where we have a string wrapped around a solid cylinder pulley here that has mass M and radius R, and suspended from the loose end of the string is a block of mass M over 2. And what we want to do today is find the angular acceleration of the pulley, alpha. Now it's all symbolic. There are no numbers, but we can work through this. So this is a Newton's law problem. So the first thing we want to do is draw free body diagrams of each of the objects. So the disk, it's a circle. Now it's important when we're doing rotation problems that we identify the forces and we identify where they act. Now gravity is our first force. That's an action at a distance, doesn't require contact. Everything else requires contact. So what touches it? The pin here in the center touches it. That's going to provide the support force, the normal force that holds it up. There is a rope touching it here. The string touches this right edge, and ropes always pull. So we have a tension on that right edge. Now we need to identify the direction of the accelerations next. Now this pulley is fixed, so its linear acceleration is 0. It is not going to translate or change position. However, it is going to spin this way, clockwise. That's the direction of alpha. So linearly, we would, since we don't have a direction of acceleration, we would use a axis that puts a lot of forces on it. That's going to be a vertical and horizontal axis. I don't think that that's going to come to matter later. That's going to, since we don't want that, we want to do the alpha, not the A. Then for the rotation, we're just going to use this central axis facing into the or out of the table. Now the block, it has gravity acting from its center of gravity, and now that's M over 2G, and it has a tension up, and that is the same tension. These are the same size force, opposite directions, because they're the same section of string. Now this block will accelerate down. It's going to go down. Now the coordinate axis system here, this translates, it's not rotating, it's just moving linearly. So we do need this linear axis, this axis. And I'm going to make down positive. Why? So that it corresponds with my acceleration. You don't have to do that. You have to reconcile the accelerations and make sure that they match at some point. I like to do it now when I'm selecting my coordinate axis, so all my accelerations remain positive, and then after this I don't really have to worry about it. So I'm going to use down as positive for the block and clockwise as positive for the disk. Both these are against the conventions, but I want them to match. And I know that if this goes down, the block goes down, the cylinder spins clockwise. So I want both those motions to have the same sign, and it's nice to work in positives. So the next step is to apply Newton's second law to each object. Here, translationally, F equal ma I don't think is valid or going to be helpful because A is 0. But the rotational equivalent of that the sum of the torques equals I alpha, that's going to help me because I want to find alpha. So there is no torque due to mg because it acts as the axis. There's no torque due to normal because that acts at the axis. They have a 0 moment arm. The only force here applying a torque is the tension. And the tension, it would be R times T times the sine of the angle, but this angle is 90, so I know that's going to be 1. It's going to equal I. This is a disk. A disk has an inertia of 1/2 mr squared. And then alpha. And that's what I want to find. So the only torque is due to the tension. The normal force acts at the axis. The weight acts at the axis. Neither of those apply torque. All right. Can't do much more there. Got an unknown T. We can use R in our answer, and we can use M. So we're allowed to use R and M in the answer, but we can't use T. Now, over here, this is translating. We want to use Newton's second law for translational motion, F equal ma. Now, again, down positive, and we're going to have m2g minus t will equal m over 2a. All right. Now we just need to solve this out for alpha. Now we have an issue here. Here's alpha, but here's a. Since this is spinning and the string comes off nice and smoothly without slipping, it doesn't specify that, but that's what's going to happen. We know that the A of the string will equal alpha of the pulley times R. So I can substitute that in here, and then everything's in terms of alpha. So I got m over 2g minus t equal m over 2 alpha r. And now we can solve these out. 2 equations, 2 unknowns, solve the system of equations. So what I'm going to do is solve this side for t and plug it in there. There's multiple ways you could do it, but that's the method I'm going to do. So here, to solve this for t, I'm going to divide both sides by r, divide that by r, divide that by r. Here the r's reduce, that one reduces that one. I get t is equal to m over 2 alpha r. Looks very familiar. Substitute that over there. I've got mg over 2 minus m alpha r over 2 equals m alpha r over 2. And now it's algebra. I can see also now that my m's are all going to reduce. Right? And put all my alpha r's on the one side. I've got, and everything is divided by a 2. That reduces. So I've got g minus alpha r equals alpha r. So g equals 2 alpha r. So g over 2r equals alpha. And there we go. Big algebra exercise there. The physics really was done right here at this point. So there. That is the end of the physics. The application of Newton's second law to each. Then after that, solving for alpha. So the problem in the textbook is similar, and this should help you solve that. Thank you very much.